We've already heard from Tony and Josh about design patterns and whatnot. Very fluffy, feely, good things about VR's future, and we saw the cool little paintball demo. And now I'm going to be the downer that just talks about really technical stuff. And if you want somebody to blame, last time I was at one of these meetups, Shannon Norrell, who I think is here somewhere, said very specifically, I want to see code. I want to see what makes this work. And so, Shannon, here you go. So, today we're going to talk about what makes WebGL or WebVR tick, excuse me, aka all the gory details that 3JS tries to protect you from, but you should probably know anyways. By way of brief introduction, my name is Brandon Jones. I work on the Chrome team. My day job is making WebGL better, more stable, faster. But WebVR is kind of my 20% project. I'm sure a lot of you have heard, that it's a thing we do at Google. And it's been really inspiring to work with people like Josh and Vlad to bring this up across multiple browsers. So everything that you see here should generally work. It should generally work across both browsers. Now, because this is going to be a massive data dump, yes, these slides are online. You can go see them right now if you want. I'll leave this up for just a few more seconds. Don't sit and try to scribble like crazy and you don't feel like you have to take a picture of every single slide because there's a lot of data to go over here. In fact, there's about 30 minutes worth of data that I have to cover in about 20 minutes. So I'm going to kind of talk fast. So, at the very outset of things, we need to be able to have a way of getting the devices that are connected to your system. Now, this may be an Oculus Rift. This may be just your phone that we're treating as a VR device. This may be some future device that we don't know about. In all cases, you're going to call navigator.getVRDevices, and this will return a HTML5 promise. Now, if you haven't used promises, then sorry, but I'm not going to cover them here. Go read up on it. But effectively, it's an asynchronous event that will come back at some point, in this case, denoted by the then operation, which we'll call this thing. Now, this is getting cut off on that screen, isn't it? Is there any way that we can poke this down just a little bit? I'll keep talking while we go. In any case, you're going to get back a list of devices. And we need to iterate over these and find out what the capabilities that we have available to us are. Now, a single device in this array is not equal to a single piece of hardware. We may have 2 or 3 different devices that all come back for a single Oculus Rift. And the devices actually represent a particular capability of that hardware. So in this case, we have an HMD VR device, which is all about, thank you, which is all about the optics of the system, the field of view, the IPD, everything that you need to know to create a correct image for the hardware that you're looking at. We also have the positional sensor VR device, which, as you might imagine, gives us information about the position, orientation, acceleration, all that good stuff. Now, how do we associate these two together? Because you might have actually multiple VR devices hooked into a computer. That's kind of insane right now, but it might happen. Is you look at the hardware unit ID, and this will associate those two devices together. Every device that represents a capability of a single piece of hardware will share a hardware unit ID. And so you can correlate those two together, figure out which device you want to use, and now we're off to the races. So, getting into the more interesting bits, a VR application at that point is simply a scene that you are rendering twice in a certain way that allows it to be picked up as the user's eyeballs as a 3D volumetric scene. If you're not doing any of the distortion to it, it looks exactly like this. This is a single WebGL canvas. We just render the scene twice using viewports to kind of wall off each eye from each other. And in order to do that correctly, and it's very important that we get this correct, because if you don't get the field of view or the IPD or anything else correct, it's going to look weird and it's going to make your user sick, and nobody likes barfing users. So we're going to go over some of the basic math to how to get this right. And once again, I'm going to skim over this pretty quickly, but these are online if you need to reference it later. First thing that we need to do is make sure that we get the correct canvas size. So now you would think my Oculus Rift has a 1080p screen, therefore I need to create a 1080p WebGL canvas, and life is good, right? No, not really. Because what we're going to do is we're going to apply a distortion to the image after we've rendered it. And that's going to cause the very center point of the image to kind of bulge out, and it's actually going to lose resolution in doing so. So by using this stuff right here, we can actually calculate an image that's the right size. It's going to be bigger than the actual physical screen size, so that when that distortion is applied, what you see at the very center of your eyeball is a 1-to-1 ratio with the pixels on the screen. So the next thing, and this is using the Git recommended iRender rect, because we're very uncreative with our naming. And you'll do it once for each eyeball, and what this gives you, going back to this page, is effectively the rectangle that describes a single eyeball in pixels on your canvas. You can also use this for GL viewport, which is shown on the bottom bit right here. Sorry, like I said, I'm going fast. Nope. Go away. Wait, sorry, got to get my bar to go away here. Wow, that really doesn't want to do that, does it? Sorry, one moment. There. Okay, so this is a whole lot of math that represents how to get the correct projection matrix for your eye. Once again, this is going to be the matrix that everything gets passed through so that it is projected the correct way onto the canvas. It is very important that you get this right. The field of view, which is just a frustum, it's described in terms of degrees. It's going out from a particular eye, and it's kind of skewed. It actually points out from your head in, at an angle. You can get that using the Git recommended eye field of view. And then you do that to it, and you get a correct projection matrix. Moving on. So now that we've got our projection matrix, those of you who are familiar with 3D already know that you typically have a projection matrix and a model view matrix, and the two of these come together to give you the correct sense of 3D in a scene. So in order to get the view matrix, now we need to start bringing in some information about where your head is actually positioned in space. Up until this point, everything has been based on the physical parameters of the device, how big the lenses are, how far away they are from the screen, everything like that. Now we're starting to talk about getting information from where you're looking. One more piece of information that we need to get from the device, though, about like the physical sense of the device, is get eye translation. Now you call this once per eye, and it tells you how far from the center point of the user's head the center point of their eyeball is. This is, once again, very important to get right, because if you fudge this factor at all, your user will either feel like a giant or a midget in whatever 3D space that you give them. And same goes for the position. So we'll talk about where the state comes from in just a moment, but the position is the actual position of your head. So if you're using an Oculus Rift DK2, not all devices will have this, but some do. You actually get tracking of where your head is offset in the world. And that comes through into this position. It has to be right, or else the user will feel like the world is just too small or too big. And it is absolutely critical that you make sure that this value and your eye offset are in sync, and that they're scaled appropriately to the world. So for example, in the Quake 3 demo that I have, which I'll try and bring up in a little bit if I have time, in Quake 3, a meter is equal to 32 units of game world. So if you're looking at the game world, you're looking at the geometry, 32 of those units will be approximately 1 meter in the game world. The eye translation that we get and the position are both given in meters. And so in order to make those positions match up with the positions of the world in Quake, we have to scale both of these numbers by 32. And that gives you something that feels correct to the user. If you don't do that, then they just feel tiny or huge. And it's very disorienting. So now this isn't like the exact math that you would have to do for your particular app in order to get the right view matrix. It's just pseudocode, but you're going to have to do something that looks approximately like this. And I want to point out one thing really quick. This is in red for a reason. Brief tangent. Quaternions are not Euler angles with an extra W component. I see this on mailing lists a lot, and it's unfortunate that it almost works. If you try this, you'll get something that looks, you can try it and you'll go, oh yeah, that looks right. And then somebody else is going to pick it up and it's going to go, ugh! And it's just going to be weird. So please, when you're doing your math like this orientation is coming back as a quaternion. Learn how that math works, convert it to matrices, do whatever you need to do. Do not treat it as XYZ rotations. I promise you that will end in tears. So, moving on. Now that we've done all that, we can actually get to drawing the scene. So I mentioned earlier we had that state object. This is where that comes from. It's the positional sensor now instead of the HMD device. You call getState on that, and that gives you a nice little bundle of what your orientation is, what your offset in the world is, and what acceleration you have. Probably won't use the acceleration too much, but it is there on devices like the Oculus Rift. So the next thing that you have to do is effectively just render the scene twice, which we can see here. You want to set up your viewport for the left eye, the matrices for the left eye, draw the scene once. Set up the viewport for the right eye, set up the matrices for the right eye, draw the scene once. And that's how you get VR. Except that's not what you actually want to do. It's a lie. It will get the job done, but I'll talk about why it's the bad way to get it done in just a moment. Now, the final thing that you need to do is on devices like this, if you're using cardboard, you're done. I mean, that's more or less everything that you need to do. But if you're using a device like this actually has its own screen in it. And your browser is probably not showing up on this screen all the time because that's a really hard way to use your browser. You can only see it halfway at a time. And you want to project the image onto that hardware. So we do that by using this extension to the already existing Fullscreen API called request Fullscreen, and you pass in this new optional array or object full of attributes. Pass in the HMD device as your VR display, and that tells the browser, I need to display this image on that headset. Thank you. And it comes out looking like this. This was the original image. This is what you rendered. And then the browser does magic, and it really is kind of magic sometimes. And it comes out looking like this on the HMD. So the benefits of doing that are the browser knows how to automatically correct for the distortion of your headset, whether that be an Oculus Rift or Google Cardboard or anything else that's going to come up. The idea is that we will be able to do that for you. We'll be able to correct things like chromatic aberration that come out from the lenses. We can do techniques like time warp, which is currently working on all the Oculus implementations of Chrome, which, as you're moving your head around, will do a last-second pulling of where the device is looking and shift the image that you rendered ever so slightly so that it more closely matches up with where the user's head is pointing. This makes a massive difference in the feeling of smoothness. We can also invoke things like direct to HMD. If you're familiar with Oculus, that's basically a mode of sending the image directly to your headset rather than treating it as a secondary monitor. And on some devices, we're still working on getting this ubiquitous. We're able to actually start throttling the request animation frame at the correct frame rate. This device renders at 75 hertz. Your computer monitor doesn't, I can guarantee you. And so in order to make sure that that comes out as not jittery, we have to render at 75 hertz as well. This API allows us to switch modes in the browser so that we start running at that rate. So now, I've talked a lot about math. This is the 3JS version of everything that we just talked about. And that's why you want to use 3JS. It really does everything for you. It's very, very simplistic. You'll create a VR controls based off of your camera that automatically tracks everything you do with your head. You create a VR effect that does all of the pushing to full screen and everything like that. And you just kind of render the rest of your scene as you would a normal 3JS app. It's really, really nice, and it gets you going really fast. And if you're just starting on either WebGL or WebVR, I highly recommend going this route first. One small caveat. I don't know if you guys have heard the joke about C++ being, if you want to build an octopus in C++, you staple legs onto a dog. Well, VR Effect is currently very much stapled onto the side of the 3JS dog. That's not to say it doesn't work. It's just not designed, well, 3JS specifically has not thus far been designed in a way that it treats VR as a first-class citizen. The render pipeline is not optimized for that. In most cases, it is good enough. But there's a way to go. So don't expect complete magic. You might need to do some optimization. Just fair warning. So given that, a couple of tips for optimizing your VR scene if and when you get to that point. And there's some of this that's available in a really awesome slide that I found on Twitter. I don't even remember who did it, sorry. But it's linked in here, so if you're looking up the slide deck, you'll be able to find it. It goes into a little bit more technical details. But a couple of things to consider. In VR, your fill rate is about the same as a normal app. Like, we're not doubling the amount of fill rate that you're using to present a scene. So if you can present a scene on your screen normally and it runs at a good frame rate, then the same fill rate for your GPU will probably work well for VR. What you're doubling is the amount of Vertex processing that you're doing. So if you have heavy-duty Vertex shaders, this is going to hit VR harder than it will anyone else, or harder than it will a normal app. But even so, fill rate can be something that is, it hits the performance hard, so be willing to reduce the canvas resolution. John Carmack said somewhere, reducing the canvas resolution in VR is almost always the right choice for performance because it's not going to look that terrible, especially on the current devices. If you have things in your scene that are not view dependent, like shadow maps, do not render them twice. Shadow maps only need to be generated once per light. This is something that I think 3JS isn't doing a good job of right now. And then finally, the pattern of set up a scene, draw one eye, set up a scene, draw the other eye is maybe not necessarily the right thing to do in VR. What you may want to do is iterate through the entire scene, setting up the viewport, drawing an object, setting up the viewport, drawing the object again to reduce the amount of state changes. This will depend heavily on the type of content that you're rendering. And so you should test it out, but it can be a useful methodology to go through. I'm going to go really quick through the last few slides because we're almost out of time here. In Chrome, the work on WebVR is still very much in progress. I think it's going to be a long time before we can say, confidently it's done. Latency is still way too high. The time warp that we have implemented helps a lot, but it's not enough. We want to do techniques like asynchronous time warp and get rid of some of the UI bits that don't really work with VR. It's an ongoing process, and it's one that we hope to continue making great strides on in the future. I'm actually not going to talk too much about this slide because and then, so Oculus Rift, by the way, there's a couple of issues that you might run into if you're trying to use it with Chrome or Firefox. You can refer to this. It's got some tricks to help you get going. Cardboard, on the other hand, the way to use that is you go get one from the nice people at the booth. There should be one for everybody here. You use it, you develop for it, and life is good. It actually works really spectacularly well for what it is. So that's everything that I have. Hopefully I haven't completely bored the audience here. One last thing that Tony wants me to show, so might as well. So this is the Chrome WebVR enabled build that you can get from one of the sites that we'll have linked on the meetup page afterwards. And you can see that I've got a VR button here. Click on that. This looks very similar to what Josh was showing. And this is basically just a scene from Quake 3 that is rendered in the browser, in VR. You know, not super complex by today's standard, but it runs really well. It's a very compelling thing when you're actually looking through this headset. The scale is right, the frame rates are good, and it just feels really good. So, you know, this is what's capable right now today with the VR. This even works on mobile, works really well actually, and you know, I think we can only go up from here. So. Thank you, everyone, and I believe now we're going to be turning it over to Leap Motion.